Okay, welcome back, folks. Okay, just realize we're heading upon the midterm exam, which is going to include the first two chapters and then this little bit of stuff thrown in. So today and tomorrow we'll finish. We're going to be working on this chapter 10, the first three sections. All right. Anybody got any questions or concerns before we get moving? Oh, and I gave a little bit extra time on that thing. I think till 12:45. So, because Brandy was telling me that she was talking to me and that it had gone over time. So, give y'all a few more minutes. Okay. Give a few more minutes, see if people get in here. Okay, so let's just go look at this definition of an experiment. Now, you'll often see this term used in science, and I'm sure people here take biology and chemistry and such, but these things called experiments are what science is all about. It's a controlled operation, okay, that yields a set of results. We may not know what the results is until we do it the first time, but it's a controlled operation that yields a set of results. Tossing a coin, rolling a die, rolling two die. There's any number of experiments that can be had, but it's just we're going to do this, and then the sample space is the total number of things that can happen as a result of doing this experiment. So if we flip a coin, there's two sides to that coin. There's a head and there's a tail. Now, we don't know when we flip that coin what side is going to come up. But we do know that one or the other of the two sides will come up. That's how probability works. We know how many winners there are amongst the sea of total outcomes. That's what probability is, finding out how likely something is to happen. Okay. So on the die, there's 6 different sides. You can see here there's a 1, a 2, a 3, a 4, a 5, and a 6. So when we roll that die, one of those 6 numbers will be showing. We don't know which one it will be, but we know that one of those 6 will be the one that comes up. That's how we calculate probability. So to find the probability of a tail, then we put the total number of elements in the denominator, the 2, and then there's only one head on the coin. So 1 over 2, or when we simplify it down to 1 divided by 2, see, that gives us the 0.5. Now just remember, for percent, you multiply times 100. So 50%. 50% is 1 over 2, or 0.5. 3 different ways to write that same number. A simplified fraction, 1 over 2. 1 divided by 2 gives us 0.5. Or we multiply 0.5 times 100, and that gives us 50%. So an event is just a subcollection of that experiment, the outcomes of the experiment. So let's just say we wanted to look at only odds. So there's 3 odd numbers there, 1, 3, and 5. So we define that subcollection so that we can then determine the probability, as we'll see in a second here. Now, probability, whether it's theoretical or empirical, the same thing happens. The denominator is always all possible outcomes of the experiment. And then the numerator is the subset for which we want to calculate the probability. Okay. So the probability of an odd number on a die, when we roll that die, there's 6 sides on it. So there's 3 odd numbers. So there's 3 over 6, and that simplifies down to 1/2. And depending on how you ask to enter it, make sure you're paying attention. If it says rounded to decimal, third decimal place, or rounded to hundredths, they will change it. It won't always be the same. Or if it says write as a simplified fraction, that's what we call an exact answer. But this could also be written as 0.5. Or 50%. Okay. So once you boil it all down to it, rolling a single die and getting an odd versus even is like flipping a coin. Half heads, half tails, half odds, half evens. All right. Now, the reason why I like to stress that empirical and theoretical probability are essentially the same thing is because the theoretical probabilities that we know about, like flipping a coin or rolling that die or anything else, are based upon this concept called the law of large numbers. The law of large numbers. And what the law of large numbers is, that means not just based upon 2 or 3 flips of the coin, but if you do it bunches and bunches and bunches and bunches of times, as the number grows, which is what this dot's showing, that it gets very close to and falls in love with and starts hugging this line, which represents 0.5 or 50%. This right here is talking about births of boys and girls. And along the X column, it's 0 through 120. And you'll see then as the number of births grow, see it gets closer and closer to that line. And most people don't have a problem accepting that men and women, boys and girls, are more or less equally proportioned at 50% each. That doesn't mean that it's like that everywhere that you go, because there are some places where there's obviously more men, some places where there's obviously more women. So, but overall, as we measure births in great numbers, they'll conform to that 50% female, 50% male. All right. This is a neat little video. I guess I'll just go ahead and play it for you. I think y'all can hear it. If y'all can't hear it, y'all can click on the link there and play it.
Braden has amazed me. He's so strong.
You hear about cancer, but you don't.
How does an insurance company decide how much to charge for car insurance? How do casinos set up payout structures to make sure that they make a profit? How does a poker player decide whether or not to fold? How do we efficiently measure the appeal of a political candidate? The answers to these questions are informed by the law of large numbers. The law of large numbers states that as the number of trials or observations increases, the actual or observed probability approaches the theoretical or expected probability. This is important to understand because it allows us to predict and have confidence in how events will play out in the long run. Let's take a common example, flipping a coin. Assuming the coin is fair, we know that the theoretical probability of flipping heads is 0.5 or 50%. However, that doesn't guarantee that if we flip a coin 10 times, we'll get 5 heads. But we can be confident that as we continue flipping a coin indefinitely, the cumulative proportion of heads flipped should get closer and closer to 50%. Looking at this graphically helps to illustrate the concept. I just flipped a coin 20 times and these are the results. After each flip, we'll calculate the cumulative proportion of heads so far. So the first flip is tails. So our current proportion is 0 heads out of 1 flip, 0%. The second flip is also tails, so now it's 0 heads out of 2 flips, still 0% heads. Next flip is tails again, 0%. Then heads, now we have 1 heads out of 4 flips, 25% heads. Flip again and it's heads, 40%. Heads again, and we finally hit our theoretical probability of 50% for the first time. Let's keep going. This graph shows the observed probability approaching the theoretical probability. One common misconception, referred to as the gambler's fallacy, is that if the first 4 flips were tails, you're more likely to get heads on the next flip because the proportion is supposed to even out to 50% heads. This is not the case because each flip of a coin is an independent event. Its outcome is unaffected by all previous events. So if you start out with 4 tails in a row, it's not that you're more likely to get heads. It's just that in the grand scheme of things, 4 tails flips will get averaged with a huge number of flips that are expected to yield an even number of heads and tails, causing the proportion to approach 50% as the number of trials increases. Another version of the law of large numbers explains that the more people from a population that you sample, so the larger your sample size, assuming your sample is free from bias, the closer your sample average will be to the population average. Let's say you have a group of 100 people. Each has some number of dollars in their wallet. We ask one person how much money she has in her wallet, we'll get our first observation, $49, which might be pretty far from the average of the group. After asking the second person, $29, and averaging that value with the first, we are likely to have a better estimate of the group average. As we continue this process of adding observations and thereby increasing our sample size, we'll generally get better and better estimates of the group's average. So the law of large numbers gives us a compass with which to navigate the randomness around us. Even though we can never predict the outcome of a single coin flip, we can know that over time about half of the flips will be heads. And in general, the principle supports the idea that a well-founded strategy that is followed consistently should win out over time, even though it might result in a few negative events along the way. Thanks for watching. See you next time. Did you think how good?
All right, so there's a nice little video that just explains the concept of the law of large numbers and how probability is essentially based upon observing all those things and the patterns that they make after doing it a large number of times. Now, here's some things that we know about probability. Okay. Properties. The property of an event that cannot occur is 0. So something that has 0 probability, that means it's not going to happen. So on the opposite end of that is the event that will occur probability of 1 means that it will occur. So the way that it looks, kind of like on a scale, a number line, there's no probability lower than 0 because that's as low as it can get. That means that it cannot happen or will not happen. It cannot be higher than 1 because 1 is the sure thing probability. That means that it will happen. And then that provides us to have this little thing, which was very much like the complement rule here. The probability of A plus the probability of not A is equal to 1. That means that both the probability of it raining, let's say today, it's 80% chance of rain. What it looks like to me, it's been raining for the last hour or so. So that means the probability of no rain is 20%. And if the probability of rain is 20%, then the probability of no rain is 80%. They're complements of one another. So they have to add up to 1. Something occurring and it not occurring will add up to 1. And that's what this right here is stating. So if we go back and look at that die, like the probability of the 1, well, there's 1 out of the 6 sides is a 1. There's 1 out of the 6 sides is a 2. 1 out of the 6 sides is a 3. Same thing with the 4, the 5, and the 6. Since there's 6 1/6, 6 pieces of pie, 1/6, that adds up to 6/6, which is equal to 1. All right. So that's where this comes from. It comes from that right there. It's what we're going to use in a little bit to talk about the complement rule. And here it is. You can look at it in one of 2 ways. The probability of A is equal to 1 minus the probability of not A, or 1 minus the probability of A is equal to the probability of not A. 2 sides of the same complement rule. So let's do some calculations on some probability. We've got a little table of blood types for different blood types, A, B, O. And then on the right is the frequency that these people came in and gave blood. 223 A people, 51 B people. 16AB, and 210O for a total of 500. Okay, so this is all occurrences as 500. Therefore, that's going to be our denominator for all of these. So the probability, we want to find the probability of AB. All right, let's put it here. All right. So what do we think the denominator is going to be here? How many total are there?
500.
Yeah, good. The big number's always on the bottom. And then the AB people are these 16. And then simplify it, 4 over 125. So if it asks for a fraction in simplified form, that's that right there. For the decimal, 4 divided by 125. Oh. And then that comes out to so that's 0.32. And what would that percent be? Well, we can multiply it by 100. So 3.2%. So 3.2% of the people that gave blood were AB. Let's see what else we got. All right, let's find the probability of O. So again, our denominator is going to be 500 because that's how many people came in and gave blood. And out of those 210, and so if we divide both of those by 10, we get 21 over 50. So 42 42%. So these are all the three possible ways you could answer this. So this is the simplified fraction. The simplified fraction would always be the exact answer to be safe. And then this one, when we divide 21 by 50, is 0.42. which is 42%. So about 42% are O. All right, so the next one is find the probability of not AB. All right. I'm going to do this one a couple of different ways just to show you about the complement rule, to remind you about it. So down here is 500. Now, the ones that are not AB, okay, so here's the AB ones. All right. So I'm going to just add up all of those that are not AB. So we can always do this. 223 plus 51 plus, so that's 484. And that's actually 0.968 or 96.8%. All right. But let's say I want to use the complement rule to get this. All right. So what I need is I need the probability of AB. So I already know that because I already did it up here. See? Here's the probability of AB. Okay. So the probability of not AB is equal to 1 minus the probability AB, which is 1 minus 0.032, which is equal to 0.968. Same, no matter which way you cut it. Complement rule, sometimes if you've got a lot of numbers to add up, the complement rule would definitely be faster. Here, it's probably not that much faster because you add up your three numbers, the 223, the 51, and the 210, and then divide by 500. Or you could just take the AB and subtract it from 1. All right. Questions about that one?
I'm a little confused, but I think the more we keep going,
Like what? Tell me what you.
I think the last part, the equals 1 minus,
Yeah, the complement rule.
yeah, that whole, like, just looking at it. I understand the first part. I just looking at this,
You
understand
mean
exactly how-
this one? You mean this one right here?
Yeah, the one where your pencil's at. Yeah.
Yeah. Okay. Because that's doing it directly. But remember, the complement rule. We've been dealing with it for in the first part of the course, and it can help us now because sometimes it might actually be shorter. That the probability of not AB is equal to 1 minus the probability of AB. And again, that's just the complement rule.
Okay, and you're just showing.
You
where
could do it both ways.
Okay.
See?
I think I'm getting it. Like I said, I think the more that we go through and I start connecting the dots, it might
Right.
start clicking.
Right.
But thank you so much.
But like I said, right here, it will sometimes be shorter because you may have a lot of numbers and it may be more trouble to add all of them up. Especially with this one. This one was kind of toss up about which was faster, but we already had the not AB, I'm sorry, the AB calculated because that was the first one that we did.
Okay.
And so,
I
and
see.
so, and rather than add all the ones that were not AB, we just subtracted from one the probability of AB, which was the 16 from 500. And that would, no matter how you do it, whether you do it as a decimal or a fraction, you're still going to come out with 484 over 500 or 0.968. Like I said, there's just a couple of different ways to do it.
Thank you.
Mm-hmm. And like I said, the complement rule is there to help you in certain circumstances where it's harder to calculate directly. That's mainly what it amounts to. All right, and this is that same problem that I was using for illustration. It was in the book, so we'll just go through it again. But the counting principle just basically tells us that if we take two experiments and combine them, then the total number of outcomes is going to be based upon the number of elements in experiment 1 times the number of elements in experiment 2. Okay, so oftentimes what's used is the M and the N. It's just traditional. So that's what the M asterisk N means. So experiment 1 is the leather and micro suede covering on the couch. And then tan, white, red, and green are the 4 different colors that each one is available in. So 2 times 4 is 8 distinct couches. So see, you got tan leather, white leather, red leather, green leather, tan micro suede, white micro suede, red micro suede, green micro suede. That's the 8. It's just a matter of multiplying. And the reason why these methods are important is because we don't necessarily need to see exactly what the elements are. We just need to know how many there are. Because when we calculate probabilities, we're just using the number of ways to do something. Now, let's say we add in a third factor. In other words, now after we've got our tan leather, white leather, red leather, green leather, tan micro suede, white micro suede, red micro suede, or green micro suede, one of those 8. Now we've got a choice to get a recliner or not. And that's all this yes, no means. It means yes, it has a recliner, no. So if you've got 2 times the 8 that was already up there, 8 times 2 gives us 16. And we can see them there. Tan leather with recliner, tan leather with no recliner, white leather with recliner, white leather, no recliner, red leather with a recliner, red leather with no recliner, and so forth. Over here, you've got micro suede green with a recliner without. So there are 16 possible ways to make these couches our own by making those 3 choices. So this is a classic one. It's you'll see a lot of them do this where you got a meal and you can pick, like an entree, a dessert, and a drink or what. Well, this one is sandwich, soup, and beverage. And there's 3 different sandwiches to choose from. There's 2 different soups to choose from. And there's 4 different beverages. So we just multiply that. 3 times 2 is 6, and 6 times 4 gives us 24. So there would be 24 different um, sandwich, soup, drink combinations here. Okay. So that's how this counting principle works. You can also use it for things like license plates. This is more or less what Louisiana uses. You got 3 letters and 3 numbers. Now, what I might try to do here is just put underneath here. There are 26 letters, right? 26 letters. So this is if repetitions doesn't matter, which it doesn't, because in theory you could have SSS or UUU or ZZZ or whatever. And then on the number side, we got 10 choices each time. Trying to put those underneath so you can see. So we're not concerned about just this one license plate. We know what that license plate says. But with this scheme, in other words, S can be A through Z, 26 choices. This one, the second one, could be A through Z, again, 26 choices. And then U, same thing, 26. And then over here, these digits is what we call them. They can be 0 through 9, which is 10 digits. So 10 times 10 times 10. Okay. And what that gives us is 17 million. 17,576,000 unique license plates. And that's plenty for Louisiana, because I think Louisiana might have, I can't remember how many. I always forget. It seems like it's around 5 million plus or minus. But that right there is enough if we had 3 cars for everybody. Enough license plates. But now let's think about California. California looks a little bit different. They got something extra. See, with Louisiana and most other states, they got 3 letters, 3 numbers. But 17 million, that's not even half of what California's population is. So they got to make sure they got enough. Well, look what they've got. They've got 1, 2, 3, 4 numbers, and then 1, 2, 3 letters. So they still got the 26 times 26 times 26. But over here, they got an extra number or an extra digit. So what does that end up being? Well, let's calculate it out. We need a calculator for that. So incidentally, like I said, is for the 3, 26 times 26 times 26. All multiplying by 10 is just add the 0 to it. And now I'm going to multiply it by one more 10. And so, see, that gets them California up to 175 million license plates that are unique. That's the counting principle. We can also like modify it to deal with repetition as well. But if there's no repetition, this right here is where we don't care about repetition, but we'll look at some of those later. All right, let's see. I was going to show you something else. I don't know what I was going to get. I can probably go over to the textbook, but I wanted to get one with a. I might have to go over to the book and get one. Yeah, let's just go over there. It just doesn't stay on as long as I want it to, so I always got to log back in. All right, we did that one. I want to do something similar. Oh, all right. I know what I'm going to do. I was trying to find something else, but we'll get one sooner or later. All right. Now, the term permutation just means that it's an order arrangements of any given objects. And the most common, the most basic one is this factorial, because these are ordered. Okay. Let me kind of show you something here. Okay. So this is where the idea of the factorial comes from. So if we have 8 books, then let's say we got them in a box and we go and pick them out. We've got 8 books. Okay. 8 books. Now, once we've pulled that book out, there's no longer 8 in there. There's 7 books in there. Once you put those 2 on the shelf, there's no longer 7 books in there. There's 6 books. Once you take one out and put it on the shelf, now there's 5. Same thing again. Now there's 4. You're just going to keep going until there are no more books. And so 8 factorial 40,320. So 8 books can be ordered 40,320 different ways. If order is important. We'll find out a little bit later when we come to the combinations. Not today. That the combinations order is not important. Now, usually what we're dealing with when we're dealing with permutations is we're dealing with a fixed group of objects, okay? And we call that N, the N group of objects. We don't know how big it is. We just know it's got N objects in it. Can be any number. Now, we're going to reach in, and let's just say they're all inside of a bag. And you could kind of think of them as individually labeled pool balls. I know and there's only like 15 or so balls, but just imagine, this infinite set of N balls in there, and then you're going to go in and you're going to pull out a handful. Well, that's what we call the R. The N is the total. The R is a handful that we're going to pull out. It can be no larger than N. If we got a hand that's big enough to go in there and pull out N object, there's only one way to do it. But if we pull out a smaller amount, how many different ways can we do it? Well, that's what this does for us. So P just means permutation. It means that order is important and that we're picking R items out of N, a smaller handful out of a total of N. And the way that we found out how many different ways there is to do that is in the numerator. It's N factorial. This is going to look sort of like that thing that you looked at that last problem. And then in the bottom is the difference between N and R factorial. Okay, so what does this mean? Look. All right. So Shauna has 17 contacts on her cell phone. In how many ways can she set up the first 4 speed dial contacts? Well, the total is 17. And then the handful, the ones you're pulling out, is 4. How many different ways can we do that? Well, let me show you. I'm going to do it by hand, and then I'll show you on the calculator. Again, a way to check it. All right. All right. So this is going to be P 4 17. And then I'm just going to make a little fraction here. And then up here, it's 17 factorial. That's the n. And then down here, 17 minus 4 factorial. So that means it's going to be and then down here, 13. Now, at this point, if you're comfortable, because you're not going to have to do with any of these, like the ones that were double. I don't know why they put those in there, but there's most of them are going to be like this, where you just got one single one over another. So you can either take a 17 factorial, plug it in, and then divide by 13. But this is the way you can do it by hand, and then you can also check it. All right. So in the top, this is equal to 17 times 16 times 15 times 14 times 1. Okay. And there's even, I mean, I'm just not putting all of them in there. I'm just showing you what the pattern is, that this would go all the way down to 2, one at a time. And then down here, well, 13 times 12 times 11 okay. Now, these are fractions, and if we have common factors from top to bottom in a fraction, and we can easily just take those out. In other words, these are going here, and then it's going all the way up to, there would be a 13 right here. So all of these back here would be gone, and down here it's simply a 1. So then this is going to be just simply 17 times 16 times 15 times 14, which is equal to 57,120. So there's 57,120 different ways she could arrange those 4 speed dial contacts out of her 17. All right. Now, let's explore the TI. See if they got a nice little video. So just to show you on the TI, you can do these things, okay? So they're going to do those too. So hit PRB.
and permutation 10, choose 5. So the way we do it is to do the combination, you type in 10,
Big number first.
and then this PRB button here, hit the PRB. When you scroll over these arrows to this NCR equals, and then you put in the last number, 5. Hit enter, that's 252. All right, now let's look at the permutation.
So the permutation is just by default on it.
You're going to type in 10, and then the PRB button, and then see if the line's already in the NCR, so you equal sign, and you type in the 5, enter, and you get 30,240. All right, so I hope the video.
So that's how you can do it on the that calculator. Now, somebody wants to figure that out and see if make sure I'm right, because I don't have a calculator handy that does that. Oh, wait a second, I got this one. All right. So it works pretty much the same way. You put in the big number. What was the? There we go. So it was. So you put in the big number. Oh, that's right. I gotta have this up to get it. So make this smaller. So 17, put in the number. Then you hit on here. Like I said, this is in the 020 class. You got that? But then it's by default on the TI. It's underneath this one.
So the PRB one, right?
Yeah, the PRB.
Yeah, I got it.
So when you hit PRB, it's by default underneath the permutations.
And what's the difference between the NCR and the PRB?
The C is
The
combination, right?
Yeah. The one with the C is the combinations. We'll go over that tomorrow.
Okay.
That's when you have no order. See here, it was order because wanted to have the first 4 speed dial contacts in order.
Thank you.
Order was important. All right. You can also do it for this. A DJ has a choice of 7 songs in the queue. He has to pick 3. So it's order. So 7. So 210 different ways. So you can do that real easy on your calculator. Now, this next thing, and this is the thing I'm going to end on, is permutations of duplicate objects. There's no specific key for that. So just kind of, you can watch the way I do it. You can also probably come up with a way to do it on the calculator. It's just that
So wait, how do you know? How do you decide that one goes by order though? He has a choice of,
because he's going to have play 7 songs. He's got 7 songs, and he's got to pick 3 of them to play after the commercial break.
so just 7 goes before the 3, like.
Well,
And
you're picking 3 out of 7.
okay.
and it's an order. And how many ways can he select the 3 different songs? The order is important. There's a cue. Uh, so permutations of of duplicate objects. Essentially, what we got to do is just divide out the ones that are duplicates. And like I said, there's no key for it in on the calculator. No calculator I know of, but I'll show you the way I handle it. All right. So let's just do Alabama. So how many different passwords can be made from the letters in the word Alabama? Now, what we got to do is we got to identify the fact that A repeats 4 times. The other letters in there are B. There's only one B. There's only one M, and there's only one A. Okay. So 4 is the only thing that, I'm sorry, A is the only thing that repeats, and it repeats 4 times. So there are 1, 2, 3, 4, 5, 6, 7 letters in Alabama. So then what we're going to do then, and here's the one that repeats, so we're just going to divide those out. If they were all unique, it would just be 7 factorial. But the A repeats 4 times, and one A is indistinguishable from the other A. So you can do that here with a regular old calculator. Oops, did I 7 factorial divided by 4? 210. So there are 210 different ways to arrange the words, I'm sorry, the letters in the word Alabama. Now, if they were all unique, then it would be just 7 factorial. There'd be 5,040. But because those 4 A's repeat, then we divide them out with 4 factorial, and that takes out the ones we don't need. All right, so that's probably enough for one day. We don't have that much to go, so I'll overlap a little bit with this tomorrow, and then finish up the combinations. If you got any questions, stick around.
Hi,
Hello.
Professor Cruz.
Mm-hmm.
So the last one that you just did, like with a regular calculator, you kind of lost me with that one.
Mm-hmm.
Just repeat what you said on a regular calculator. What would I hit? By I put in
Seven,
the
the
biggest number, which is
7 and the
7.
factorial key.
Mhm.
The 7 and then the factorial key. It should be under the PRB, I think. So
Yeah,
hit 7.
and then you gotta hit the little arrow to the right to
Got
change.
to go over. I think it's the third one, right?
Mm, okay.
Yeah, it's
And
the
then
third.
you hit that. You put in that, and then you hit divide, and then you put 4 PRB, and then scroll over again.
And whenever you hit equals, it'll give you the answer. So with the Alabama one, why wouldn't I just do 4, like ALBM factorial? It needs to be 7.
Well, but there's 7. There are 7 letters in Alabama, but you're essentially dividing out 4 of them that are repetitious.
Okay.
So that's what you're doing when you divide that by 4. The 4 are the ones that repeat, and they're indistinguishable from one another.
Okay.
So therefore, that's why we divide them out, because it doesn't matter which egg comes first if you got them rearranged. Oh boy. Did you get it, Chantel?
Yes, thank you.
Okay.
Thank you. Y'all have a good day.
Okay. See you tomorrow.
Okay, y'all take care.
Uh, it's right here. Look. Oh, you already left.